Here's a quick video on how to graph some of these logarithms and some of its properties. So, really fast you can tell this is a logarithm with base 2. And remember, just like all the other functions, all these things here just create different shifts and movement on the graph. But the parent function of logarithms are going to be based off of the base, and then all logarithms have this vertical asymptote that's involved with them. And remember, they also all have this point at 1, 0. And on one end, they approach the asymptote. On the other end, they curve up, kind of like a hill. And you can always use a table to get a more precise graph, but this is the initial idea. And remember, any transformation that's inside, so this is the argument of the logarithm, and the inside part, plus 3, remember, does the opposite of what you would think. So instead of going right, it's actually going to go 3 to the left. So that same point at 1, 0 is moving 3 units to the left. So it's going to be here now. But if that's moving to the left, your asymptote also has to move to the left. That's what's going 1, 2, 3 to the left. And the point 1, 2, 3 to the left. But the shape is still the same. I mean, we're going to copy the shape. And it's going to be exactly the same. Oops. It's all the exact same shape. Just shift it over to the left a bit. Let me change the color to be able to match. And then this -2 just moves everything down. Everything outside does a vertical transformation, and everything inside are horizontal. So this vertical asymptote going up or down doesn't change its location. It goes up forever and down forever. The only thing that's moving is this graph a little bit. So just going down 2, it's going to be here. But still the same graph. You approach the asymptote. And then it curves up. And that's it. Move left 3, down 1. Here's another example. Again, we look for the base is 3. That means we're doing log base 3 of x. And all that's changing as this base is getting bigger, the cells log base 4 or 5 or 6. It also has the same shape, but as that base gets bigger, this just gets further, I don't want to say narrower, but it looks like it's turning faster and getting closer to that asymptote. That's all that changes when you go from log base 2 to 3 to 4. And I can show you here really quick on this graph. You can do logarithm. You can do log base 2. Log base 2x. Log base 3x. log base 4x. And again, you can see as it just goes, that is 2, 3, and 4. It's just getting lower and lower and lower, but still has the same overall shape. And if you notice, they all have that same point at 1 comma 0 to start with, right? It could shift left, right, up, down, but the first initial point is right here at 1 comma 0. And once again, same overall shape, just comes down a little more. And then, remember inside, you have to start with inside first. This shifts it to the right because it's opposite of what the here. But so does the asymptote move to the right as well. I'm just going to copy that shape. That's still the same. I'll change the color. And then the negative. So before you go with this one, you go with something multiplying outside. So this didn't have, it was positive, so you don't have to worry about it. But this one, because of that negative, we have to make a reflection on the x-axis, which means the graph is going to reflect. So this point's still here, but whatever was below the x-axis, think about just making a mirror and flipping it. So this part came up, this part went down, and that's the reflection on the x-axis. And lastly, that 1 just shifts everything up 1. So that's going to look like this. Up here, same idea. Ran a little bit out of room, but same concept, right? Keep going that way. So just curves, 2 to the right, reflect, up 1. And just some properties to memorize about a logarithm. And again, all these are still based off that. You can get all these properties based off that original one that tells us log base b of x is equal to y is the same as rewriting it as b to the y equals x. And you can, and the idea is because here we're saying that if you have 1 in your argument in any base, that logarithm's always going to be equal to 0, which makes sense. Because if I rewrite this into this exponential form, this is saying b to the power of 0 is always 1. And we already know that property is true. But this is a way that you can memorize it when it's in the form of a logarithm, so you don't have to rewrite it into that exponential form. Same thing here. This is saying that if the argument and the base are the same, it's always going to be equal to 1. Log base 4 of 4 is 1. And this one above, log base 3 of 1 is 0. And this is saying if your base and your argument are the same, that means, and if there's an exponent, which is pretty much a more general sense of this one, because this has a power of 1 equal to 1. Whatever power is here This is what equal to. Log base 3 of 3 squared is equal to 2. Which 3 squared, this is the same thing as saying log base 3 of 9 is equal to 2. Again, you can rewrite this with a base of 3, so you can see the answer is 2. Or you have this odd version of the logarithm when there's this base and in the exponent there's a logarithm that has the exact same base. It's saying that the logarithm is equal to the argument. So 2 to the power of log base 2 of x is equal to x. And these are the general properties. There's more specific ones. For example, this is a very specific logarithm that's known as a natural log. And that's because it has a very special notation. The notation is that the base of the logarithm is e. And if you don't know what e is an irrational number that roughly is 2.7. Similar to the idea of like pi is 3.14, 1, 5, and it goes on forever. So is e. It's very special exponential. Which still falls under the same type of logarithms we're looking at. Because we've been looking at the logarithms that have a base that's bigger than 1. E is 2.7, so that is bigger than 1. But it has a very special notation. Instead of writing log base e of x, we just put ln of x. And we don't write the base, but when you see ln, you know it means log base e. Right? So for example, ln of 1 is just a very specific version of this property. We're just saying log base e of 1. Which is this says any, regardless of what the base is, if your argument is 1, it's going to be equal to 0. So ln of 1, 0. Now this is ln of e, which in other words, it's log base e of e. So the base and the argument are the same, should be equal to 1. Here, I know the base is e, the argument is e, and has an exponent of x. Hence, it's equal to the exponent. And then e to the power of ln, which is just e to the power of log base e of x. Again, a very specific version of this example, which is log base e of e is going to be equal to the argument, which is just x. It's just a very common logarithm that gets used. And this is a logarithm that you see on your calculator as well. So it's good to memorize that. Similar to, like for example, when the square root of x, we know the index is 2, but we never write it. So ln of x, we know is log base e of x. We just don't write it that way. There's one other logarithm that's similar, and that one's known as the common log, which tells us instead of writing log base 10, we just write log of x. So we just don't write. Same thing as the square root, how we don't write the index. Here we just don't write the base. So if you see something that says just log of 1, you know this is actually saying log base 10 of 1, which is equal to 0. Because anytime your argument is 1, it's always going to be 0. This is log base 10. We don't write it of 10. Since they're the same, it's equal to 1. Here we get 0. Here we get a 1. This is the common log of 10 to the x is x. And again, because this is technically saying log base 10 of 10 to the x. The base and the argument are the same. It's equal to the exponent. We just don't. You have to get used to not seeing it there, but know that this is more what it's saying. Or 10 to the power of log of x. Once again, we don't say or show the 10, but we know it's there, which these two are the same. It's equal to the argument. And then sometimes there's some logarithms that we can't figure out. And that's why we need the natural log and the common log sometimes. Because our calculator has those two logarithms. And you can use this change of base formula. For example, if we rewrote this log into exponential form, right, it would be 2 to some power is equal to 3, which we don't know how to find this. But the change of base formula says that you can rewrite the logarithm as two logarithms dividing each other, and you can choose a base. And then the argument of the logarithm is still the argument in the numerator, but the base of the logarithm becomes the argument of the logarithm of the denominator, and you choose a base you want to use. Like, for example, you can choose base e. So you can turn this into log ln of 3 divided by ln of 2. Or the common log of 3 over the common log of 2. And these numbers exist in your calculator. You could just, or ln exists, you could put ln of, and then put 3 divided by ln of 2. And that can at least get us something. It's going to be some irrational number, but it can still find us something that we can't do by hand. This is where this exponential form is not as useful. And a couple more properties that are beneficial is just some expansion properties of the logarithm. That if you do see multiplication in your logarithm, you can expand it to two separate logarithms adding each other. If there's division, you can separate it to division. And if there's an exponent, you can write it as a coefficient. And for the subtraction, it's very specific. You subtract by the denominator. And then here, a quick example of expanding. You have to recognize there is multiplication going on. And that's going to be, because of that multiplication, at each multiplication, you're going to be able to expand it to ln of e plus ln of x plus ln of y. And remember, we just talked about this ln of e, because I know this really means log base e of e. When the argument and the base are the same, we know this is going to be equal to 1 plus ln of x plus ln of y. It just helps you expand the logarithm. Here's another quick example. And if you remember, make a quick note. You can always write any rational exponent as a radical or vice versa. So here, because how do I separate? I know there's multiplication here, but I need to get rid of that radical. And I can do that by rewriting this as 4x to the 1/2 power. Because the base is 2. The index is 2. You don't write that for the square root. But the base, the denominator, is the index. So this becomes the index. And this altogether has a power of 1. And that's your numerator. But remember, if you have a power, you can write it as a coefficient. So this becomes 1/2 log base 2 of 4x. Now I can separate that multiplication as log base 2 of 4 plus log base 2 of x. And if you notice, I put it in parentheses because this half was applied to the entire logarithm. So as it expanded, I'm going to have to distribute that logarithm to both of them. But here, because I know the base and I know the argument, I can simplify this. And again, you can either remember how to, you rewrite it as exponential form, which is 2 to some power is equal to 4. We know that's going to be 2. So in other words, log base 2 of 1/2 of log base 2 of 4 is going to simplify to just 2 plus log base 2 of x. Then I'll distribute that 1/2, and now it's going to be 1 plus 1/2 log base 2 of x plus a half times 2 simplifies to 1. And then here, there's multiplication, right? There's a power, but that power is not applied to all of them, so I can just take care of the multiplication first. Log base 4 of 1 over 16 plus log base 4 of t cubed plus log base 4 of v. Now, here is a fraction. You can either try to rewrite it into exponential form to figure out how to get this value, or you can use that property. It's log base 4 of 1 minus log base 4 of 16. And then this power, you can write it as plus log 3 times log base 4 of t plus log base 4 of v. And then anything, remember when the argument is 1, this is just going to be equal to 0. And then here, you can rewrite this as 4. You can write the 16 as 4 to the power of 2, which is log base 4 of 4 to the second power. So remember, when the base and the argument are the same, this is just going to simplify to the exponent plus 3 log base 4 of t plus log base 4 of v. And then 0 minus 2 is just going to leave us with negative 2 plus 3 log base 4 of t plus log base 4 of v. And one big example, again, we have to take care of the fraction first. That's going to be log base 2 of square root of z minus log base 2 of xy squared. And again, this square root can be rewritten as log base 2 of z to the half power. It's important to remember how to rewrite a square root to its rational exponent. This we can expand as log base 2 of x plus log base 2 of y squared. And I put it in parentheses because this whole logarithm was negative. So if I expand it into 2, I need to remember to distribute that negative to both. This exponent can be a coefficient. It should be 1/2 log base 2 of z minus log base 2 of x minus, and same thing, this 2 can come out in front. It'll be 2 log base 2 of y. Because I don't know the argument in any of these, I can't simplify it any further than this. There's just some quick ways of graphing some properties for the logarithm.